I hope my screen is visible. Type yes in the chat box. Can someone type yes in the chat box if my screen is visible? Okay, Ganesh. Thank you. Okay, let's start discussing more about the ranges. So, yesterday we have just started discussing about the primitive data types and the whole concept of the number conversion from decimal to binary number system. So, the binary number systems, the number system needs to be understood so that internally the computer stores data in the form of binary number system. It is going to use binary number system to store any kind of data, right? So the data can be represented in many ways, but if you talk about primitive data types, this particular thing, primitive data types are categorized into 8 types: byte, short, integer, long. Right? These are going to store the whole numbers, and these are the ranges, the range of values that you can store using each and every individual data type. These are the range of values. For byte, the range starts from -128 to +127. So these are the given ranges, and float and double, they are also used to store the data, but the precision values, the exact decimal representation. You can store the data in the form of the exact decimal representation. The fractional part can be stored by using these two data types. Again, these two data types, the Boolean data types is used to store either true or false, the 1-bit representation. Character data type, char data type is used to store any letter in single quotes, any character in single quotes, right? So let us understand this one by one. Let us understand about these numbers, how these numbers are arrived actually, right? When they say 1 byte of memory, so this 1 byte of memory can store data ranges from, can store a number that is specifically ranging from -28 to +127. So how this conclusion has been arrived, we will understand that today. So we do not really necessary to memorize these numbers. Instead of memorizing this number, we will try to get the answers by some mathematical calculations, so that it is not required for us to do the memorization. So let's get started. Right. Byte is a data type. So before even understanding about these numbers, there is a formula. We have a dedicated formula, a typical formula to perform these calculations. So 1 byte is also can also be represented as collection of bits, collection of 8 bits. So I can indirectly say that 1 byte is equivalent to 8 bits. When I say 1 byte, it is equivalent to the collection of bits, which is nothing but collection of 8 bits. Collection of 8 bits is going to be a byte, right? So for any collection, for any number of collections, for if I have n bits, if I have, let us say that if I have n bits, the formula for calculating the range for n bits is going to be -2 to the power of, okay, let me write this. The formula is going to be minus 2 to the power of n minus 1. So here n is representing the number of bits. Minus 2 to the power of n minus 1 to plus 2 to the power of n minus 1 minus 1. Okay, this is the formula that has been discovered or that has been evaluated by using some algorithms. You will understand about the algorithms. But if you substitute this formula for this particular byte data type, so 1 byte is going to be the 8 collection of 8 bits. So just substitute this 8 bits on top of n, replace n with number of bits. If I do so, the values are going to be like minus 2 to the power of 7 to plus 2 to the power of 7 minus 1. After further evaluation, it is going to be what? Minus 128 to plus 127. So this is the range. This is the range for the byte data type. Likewise, if you go for if you ever had to calculate the range for short data type, same formula. Just find the n. N is nothing but the number of bits. How many bits are there in short data type? Very simple, isn't it? How many bits are there in the short data type? 2 bytes. 2 bytes in the sense 16 bits. Just substitute 16 in place of n. You will get the value. Values are going to be what? Minus 32,768 to plus 32,767. Okay, everything is okay. So we know the formula. So from the formula we can evaluate the results. We can find the ranges. But how this formula has arrived? The question is how they have arrived. How they have discovered this formula. What kind of algorithms and what kind of pattern is behind this formula? Is hiding behind this formula, that we will understand now. Right. So in order to understand that, let us we four together we are going to design a new data type. So these are the predefined data types, and to understand this further, we are going to create our own data type. What we are going to create? We are going to create our own data type. Our data type name is going to be something like, let us say that the name of the data type is going to be moon. Our data type is going to be one. So in our data type, so it's just like, we are just trying to design our own data type. So if we ever get a chance to design our own data type, right, and the recommendation is like the data type size should be half byte, not 1 byte. The size of the data type should be half byte. Just an assumption. What? Half byte. Let me write that over here. Half byte is equivalent to 1 byte is equivalent to collection of 8 bits. So half byte is equivalent to collection of 4 bits. If I convert this formula, if I show these memory allocations in the real time, this is how it looks like. 4 bits are going to be like this. 1, 2, 3, 4. So how many sets of data, how many combinations I can save by using this 4 bytes? Let us try to calculate the number of combinations that you can store, number of values that you can store by using this 4 bits. It will not take much time. It is going to be very easy. By using 4 bits, I can save 15 combinations of data. 15 combinations of data. So what are they? The first combination starts from 0. The combinations are going to be like 0, 0, 0, 0. First combination is 0, 0, 0, 0. Second combination 0 0 0 1. Likewise, it keeps going 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1 1 0 0 0 1 0 0 1 1 0 1 0 1 0 1 1 1 1 1 0 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. These are the possible combinations. Totally we have 15 numbers. The number starts from 0. This number is representing 0. This number is representing the decimal number 1. It is going to represent 2. Likewise 3. And it keeps going till all numbers, all the bits are 1. And then the equivalent decimal number is going to be what? 15. Right? So when I say, if I have decided a data type and the name of the data type is 1, right, and it is going to have off byte of memory. Off byte of memory is equivalent to 4 bits. When I say this, it means I can store the numbers from 0 to 15. And if you observe one thing, I am able to store only the positive numbers. In this case, I am able to store only positive numbers, but my requirement is I should be able to store the positive numbers as well as the negative numbers. That is my requirement. But in this case, I am able to store only the positive numbers, right? But if I ever add given a requirement, or if I ever add given an option, or if I ever add given a requirement to store the negative numbers as well, I need to consider some situations, some cases, some scenarios. So we as a developers, we as human beings, we can able to differentiate a positive number and negative number, or the numbers can be distinguished between the positive number and negative number with the help of symbols, right? Okay, when I say plus, it is a positive number. When I say minus, it is a negative number. We humans, we understand that. But if you want to represent the negative number in the form of binary numbers, we need to follow some pattern, right? Computers understand everything with some patterns. So this can be distinguished, the negative numbers can be distinguished by computers with the help of 2's complement. So let me reiterate this. You must be wondering why we need to discuss all this, because these are the fundamentals. So understanding this will make more sense in understanding the data types. Trust me, after 2 classes, you will get to know why these things are necessary. So yeah, the question is, if we ever had to differentiate distinguish a negative number and positive number in the form of binary numbers. Distinguish number and a positive number in the form of binary numbers, we will have to convert the number in the form of 2's complement. And the follow-up question is going to be, what is a 2's complement? 2's complement. So what they have concluded that if we have an n number of bits, in this case we have 4 bits, right? 1 2 3 4, 4 spaces. It is also called as 4 bits. The first bit can also be called as MSB. MSB means it is an acronym for most significant bit. First bit, I am talking about this first bit. We call it as MSB. MSB means most significant bit. Most significant bit, right? The conclusion is very simple. If the MSB is 0, if the MSB is 0, it means a number is a positive number. If the MSB is non-zero, which means if the MSB is 1, it means the number is representing what? Number is representing a negative number. Very simple. When you see any number that is stored in the bits, that is stored in the bits in the form of binary number system, the most significant bit is nothing but the first bit. The first bit from the left side. The first bit from the left side is going to represent the most significant bit. If the MSB is 0, the number is a positive number. If the MSB is 1, the number is going to be a negative number. How this conclusion has happened, we will discuss about that now. So let me reshuffle this. So let me take all these sets and do some reshuffling. So I am taking all the zeros, all the MSBs at one side. 1 minute. So I am taking all the negative numbers in the sense we are assuming that if the number starts with 1, if the first bit is starting with 1, it is a negative number. If the first bit is starting with 0, it is a positive number. It is just an assumption, and I have just divided this sequence. So all the numbers that starts with 0, I have placed it in the right direction, and all the numbers that starts with 1, I have placed it in the left hand side of my towards the left hand side of this. Right, a small differentiation. Right, what they say, just find the 2's complement. Just find the 2's complement of the particular binary number that starts with 1. Right, if you just convert this directly, what you will get? Direct conversion. If you convert 0 0 0 0, right, the answer is obviously going to be 0, and this is going to be equivalent one number. It is going to be 2. It is going to be 3. This is going to be 4. Right, likewise this is going to be 5, 6, 7, right? And if you come here, if you convert directly without even considering about the negative numbers, it is going to be 8. Direct conversion is going to be 9, 10, 11, 12, 13, 14, 15. This is a direct conversion, but what they are saying is, don't do this conversion directly. If you find the first most significant bit is 1, try to find the 2's complement, then do the conversion. Right, if I try to find the 2's complement of this particular bit set, right, so 2 complements is very simple. The number is 1 0 0 0. Right? If I ever had to find the 2's complement of 1 0 0 0, I am asked to find 2 complement of this number. Firstly, I will have to find the 1's complement. 1's complement is nothing but flipping the numbers. If it is 1, flip it to 0. If it is 0, flip it to 1. 0 1 0 1. So this is called as 1's complement. Right? 2's complement is adding a number 1 after the 1's complement. You will get the 2's complement. Just add a number. Add 1 to the 1's complement. Right? If I ever try to add this, right, the answer is going to be 1 plus 1 is 10. Carry 1. 1 plus 1 10, carry 1. 1 plus 1 10, carry 1. 1. Right, now convert this into decimal. So how do you convert this particular number to a decimal number? Just raise the power, raise the 2 significant of the powers, like 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Right, if you find this 2 to the power of 3, the answer is going to be 8. Right, since it is starting with 1, add negative. Right, so this is what? Minus 8. Go back there, instead of positive 8, just use minus 8. That's it. Okay sir, if you are saying this, and what output you are going to get for this particular set 1001, right? Same calculation 1001. 1 0 0 1, right? I need to find 2's complement to get the negative number. Before finding 2's complement, first of all I need to find the 1's complement. 1's complement is nothing but flipping the numbers. If it is 1 0, if it is 0 1, if it is 0 1, if it is 1 0, this is 1's complement, right? Adding 1 to the 1's complement is nothing but getting the 2's complement number. To get the 2's complement, first convert it to 1's complement and add a 1. Right, now you perform the addition. 1 1 1 0, right? Do the decimal conversion. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, right? If you directly do the conversion, 4 plus 2 plus 1 equal to 7, right? Since it is a, the MSB is 1, add a negative sign to it. So you're going to get what? Minus 7. Right? This is not 9. This is minus 7. According to binary, according to the most significant bit logic. If you want to represent a negative number, what you will have to do, you have to consider all the most significant bits. If it is starting with 1, right, do the 2's complement. After doing the 2's complement, you will get a number. Add a negative sign to it, right? Likewise, if you do the conversion, this 10 is going to be what? Minus 6. 11 is going to be what? Minus 5. Minus 4. Minus 3. Minus 2. Minus 1. Right? If you talk about the range, now you see the range is starting from minus 8 to positive 7. Right? The range is starting from what? Minus 8 to positive 7. I can also write this like minus 2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. Right? Here n is what? N is what? The number of bits. In our case, number of bits are, we have 4 bits. 1, 2, 3, 4. 4 bits, right? So minus 2 to the power of 3 to 2 to the power of 3 minus 1. Right? If you calculate this, the range will be like minus 8 to plus 7. Right? This is the range value calculation for our data type, which is as per our assumption, we are considering a data, we are trying to discover a data type. The name of the data type is our own data type. Right? Same logic applies for the byte data type. Right? If you take byte, same logic applies. Right? Byte data type is going to be a collection of 8 bits, right? And you will be writing 8 bits in this format, like 8 bits, right? And whenever you are finding any bit, if the most significant bit is 1, you will do 2's complement, right? If the most significant bit is 0, you will do nothing, direct value. If the most significant bit is 1, you will do 2's complement to get the negative numbers. The conclusion is very simple. If you ever had to get a negative number, right? If the computer or if any memory, any RAM memory, if it ever has to store any negative number, it will consider the negative number according to the MSB, most significant bit. If it is 1, it performs 2's complement and it will get a value and it will attach a negative sign to it, as simple as that. Right? If I want to store only the positive numbers, this conversion is not required. Directly I can store. But my requirement is I want to store the negative number as well as positive number. If that is the requirement, if that is a requirement, I need to use the concept called 2's complement concept. 2's complement concept is going to fetch the negative numbers from the most significant bit. Able to understand? Just type as in the chat box if this logic is understandable, or you are finding it little confusing. It's just a logic to arrive to the conclusion about that specific formula. Are you able to follow? Darshini, first one. Type yes in the chat box if you are not able to understand, say something. Okay. But how 2 to the power of 3 is 4? No, 2 to the power of 3 is 4. I didn't say 2 to the power of 3 is 4. 2 to the power of 2 is 4. 2 to the power of 3 is what? 8. But here the bit value is 0. So this calculation is not required, isn't it? 2 to the power of 2 is 4. How did you find that? 2 to the power of 3 is 8. I never said 2 to the power of 3 is 4. You can unmute and talk, Darshini. I mean, which part you're talking about? I'm okay. Okay, no worries. Okay, no worries. Very simple, right? If you ever had to design your own data type, right? This is just an assumption. These things are not there. These things are not there. I mean, there is no concept called the own data type. This is for our understanding. Very simple. If you ever add a requirement to design your own data type, right? And the requirement is like you need to design a off byte data type. Off byte data type is equivalent to 4 bits. 1 byte, if the 1 byte data type is a collection of 8 bits, then off byte is going to be what? 4 bits, isn't it, right? So 4 bits can occupy the values that is ranging from 0 to, right? It keeps going. If you do all the permutations, you can the possible ranges are from 0 to 15, but all are positive numbers. But my requirement is I should be able to store the negative numbers also, right? We as humans, we can able to differentiate a number whether it's a positive or negative depending upon the signature, depending upon the sign, right? But for computers, that differentiation is possible with the help of MSB. MSB is nothing but most significant bit, right? This most significant bit, the first bit of any binary number, first bit is talking about what? The most significant bit. If it is 1, right, add a negative, attach a negative sign. If it is 0, attach a positive sign. As simple as that. Before even attaching a negative sign or positive sign, first try to find the 2's complement. After finding the 2's complement, you will get a decimal number, isn't it? A decimal number will be thrown, or decimal number can be what we call it as a decimal number can be built out of this 2's complement number. After getting the decimal number, attach the symbol. If it is 1, attach a negative symbol. As simple as that. If you do that, right, the actual numbers are like 0, 8, 9, 10. These are the actual numbers. Without 2's complement, these are the actual numbers. 8, 9, 10, 11, 12, 13, 14. All positive numbers. Right? If you do 2's complement, you will get the negative numbers in the decreasing order. So for 8, you will get -8. For 9, you will get -7. For 10, you will get -6. For 5, right? From this pattern, if you see this pattern, the pattern is talking about the formula that we are actually talking about, right? This is the pattern. -2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. This formula is now proven for both negative numbers as well as for the positive numbers, right? So our own what we call it as our own data type is of size of byte. Of byte is also, it is equivalent to 4 bits. Just replace this 4 bits on top of n. You will get the range. Range is like -8 to +7 for our data type. And same, substitute the same what we call it as same bits. You do the same substitution for all this, right? If you talk about 8 bytes is a collection of 64 bits. 32 bits. I'm sorry, 8 bytes is a collection of 32 bits. Sorry, 64 bits. 8 into 8, right? 8 into 8 equals 64 bits. Right? After performing calculations, the negative number is going to be this much big and the positive number is going to be this much big. Even if you want, you can memorize this, but memorizing is not an option. But the right thing is for us to understand how these numbers are arrived. Making sense? If you have any doubt, just repeat this video once again. You will get the clear understanding about these ranges. For now, just understand what is MSB, most significant bit, and what is 2's complement. So 2's complement are used to find the negative number. As simple as that. If any binary number starts with 1, the 1 is representing a negative number. If it is starting with 0, the 0 is representing a positive number. As simple as that. Right? We will see. We will analyze few more examples, and this concept will be crystal clear after some examples. Right? Shall we proceed to the next part? Right, and see, from this methodology, from this concept, we will be able to calculate the ranges for byte, short, int, and long. Right, and again, it is very easy for us to calculate the range values for 1 bit boolean. When you talk about boolean is representing a storage capacity of 1 bit. 1 bit means only 1 bit. In this 1 bit, you can either represent 1, or you can either store 0, or you can either store 1. Right, so 1 always talks about true, is equivalent to true. 0 is also equivalent to what? False. As simple as that. So this is the, when someone is asking you what is the list, what is the data type that is going to have the less memory, that is going to store the less memory, you can simply say that boolean data type. Boolean data type is such data type, it is going to store, it is going to have only 1 bit of memory. At any point of time, you can able to store two potential values at any, one potential value from two possible combinations, which can be true or false. True or false. This is the lowest data type that anyone can come across, which is boolean. Right. So now we will try to understand about some operators. Let me save this. There is a concept called bitwise operators. Bitwise operators. So there are many bitwise operators that is available in Java. You can perform some binary operations by using bitwise operators. Right. So understanding these operators is like understanding the internal functionality or internal calculations of a particular program. Right. When you want to evaluate or when you want to perform some operations with Java, internally Java is going to use the bit calculations and bitwise operators. How it is going to use, that we will understand. First of all, let us analyze what are the some prominent bitwise operators that are available in Java. Let me list it out here. So first one is bitwise OR. Bitwise OR, and it has its own symbol. So this is the symbol for bitwise OR. Second one is bitwise and the symbol is ampersand. And we have a bitwise XOR operator. The symbol is a cap symbol. And we have bitwise complement operator. Complement, and this is the symbol. And we have left shift operator. Left shift. Two angular brackets pointing towards left. And we have right shift operator. We can say right shift, or we can also say signed right shift, or we can also say arithmetic operator. So we will understand this with these two terminologies. This is a symbol, and we have unsigned right shift. right shift. So we have like three angular brackets pointing towards the right side. These are the bitwise operators in Java, right? So each and every bitwise operator, they are going to perform some calculations, right? So before even understanding about the calculation, we need to understand a concept called truth table. I know very well that you might have come across about this truth table. Truth table are always going to talk about take two inputs and it is going to do some evaluation. So all the inputs will be in the form of binary zeros and ones. Two inputs and an output, right? The output is based upon the bitwise operator. What does it mean? Let us say if I have an input A, if I have an input B, when I say A or B, when I use the bitwise OR operator, bitwise OR operator is like A, this is the symbol for OR, A or B. I know very well that you people know all this and you might have come across this in your school academics, right? But let us just revise. This understanding is important. So when I have inputs like 0, 0, 0, 1, 1, 0, 1, right? When I say A or B, the calculation is very simple. OR means if at least one bit is 1, the output is going to be 1. At least one bit. Right? In this case, A and B. A is 1, B and B is also 1. So directly 1. And in this case, A is 1, B is 0, 1. At least one bit is representing 1. The output is evaluated to be 1 or else 0. Right? This is a typical truth table for bitwise OR operator. This is the symbol. Or I can also say OR operator. Right? For example, if I have a requirement to calculate two numbers, for example, let us say that I have two numbers. Write A equal to any random numbers we can take. Write B equal to 9. I want to find A or B. A or B. So let us trace this output in the Java, then we will understand how this gets calculated internally. I don't think I need to give you more explanation. Let me use Java Online Compiler. So for the time being, I'm using Java Online Compiler, and we already had a big section on how to download Java. If you have any queries, you can refer to those videos. I will be okay. So this is simple typical Java class. The name of the class is hello world, and let me take two inputs. Byte A equal to, so same information I am taking. Byte A equal to 5, byte B equal to 9. A equal to 5, byte byte B equal to 9. System dot out dot println. If I ever had to find A or B, this is the symbol for all. A or B. Very simple. 9. So the output is 13. We get output 13, and we will analyze why the output is 13. But if you want to talk about this particular program, the program is very simple to understand. Have a class, right? Whatever the logic that you want to write, you are forced to write your logic inside a class. You can take the name of the class as any meaningful name, right? Still we haven't started discussing about what is class, what is method. So these topics are the future topics, but For the time being, just you will put all the logics inside a class. Without class, you cannot draft any logic. Whatever you want to write, you have to write within a class. That is the rule, right? Not within a class, and you need to declare everything inside a method, main method. Right here, I am like saying declaring a equal to 5, b equal to 9. Let us trace this. When I say this, what happens internally? We are talking about the internal things. After compilation, so two major things happens internally. First thing is this code. This is what we call it as the source code. This part is called as what? The source code. Why source code? Any code that is written or that is created or that is developed by a developer. Any code that is developed by a developer or written by a developer, we usually call it as what? Source code. This part is called as what? Source code. Source code. So the source code needs a compilation. Why compilation is required for the source code? To check if there are any errors present inside this code. If the code is error free, right, the code is eligible for execution. It gets eligibility for the execution. So compiler will take care of what? Compiler will take care of corrections. This code, the source code will be converted to what? Dot class file. Very simple. You can save this code with .java extension. If you don't know what is .java extension, I think in the 5th video there is a big section on this for .java. You will have to save any code in Java with the .java extension, and the name of the file should be same as the class name. Here the class name is hello world. Hello world.java. This hello world.java will be, this particular file will be sent inside the compiler. 1 minute. Okay. Hello world.java, it's a source code. It needs a compilation. Compilation will ensure that the code is error free. This will be sent into the compiler. Compiler will perform compilation. After performing the compilation, it will produce a .class file. .class file is very simple. It is a file that is generated by a compiler for further execution. So the file will be converted from .java to .class. Hello world .class. So the .java file is converted to .class file. Then the JVM comes into picture. So this is the JVM. JVM is nothing but Java Virtual Machine. Java Virtual Machine. The job of the Java Virtual Machine is to execute and is to allocate memory. Java Virtual Machine. So Java Virtual Machine will take what? Will take .class file. So this is the .class file. This .class file will be loaded into Java Virtual Machine. Right? As soon as .class file is loaded into the Java Virtual Machine, this Java Virtual Machine will create a thread. Thread is nothing but it is a kind of it acts like what? It acts like a control. Okay. This thread will try to get access to the main method. The job of the thread, this is called as a main thread. Very simple, guys. This .class file will be loaded inside the JVM. These are internal things. As soon as the .class file is loaded, the main thread will be created. This main thread, the job of the main thread is to execute all the instructions inside the main method. So this is the main method, right? Any method with the name main is called as a main method. All instructions has to be executed by the main thread. So the control will be transferred from here to here. So what the first line says? First line says the data declaration. From the first line, the main thread is going to allocate some memory. What memory it is going to allocate? Byte of memory. Byte is nothing but 8 bits, right? So 8 bits of memory will be allocated. 1, 2, 3, 4, 5, 6, 7. So 8 bits of memory gets allocated. right? And what is the value? Value is 5. 5 is a decimal number. It has to get converted into what? Equivalent binary number. What is the equivalent binary number of 5? 2 2's 4, 1, 2 1's 2, 0, 1 0 1, 1 0 1. So this is A. So this is how the memory gets allocated internally inside the RAM. So the 5 will be converted into the binary number, and this is how the memory gets allocated internally. Okay, first line completed, and the control will be transferred to the second line. In the second line, we are saying byte B equal to 9, right? Again, same memory block. Byte is going to allocate 8 bits of memory, right? 8 bits of memory. What is the variable name B? Isn't it? B. What is the value 9? To convert the 9 into the equivalent binary number, 4's are right, balance 1, 2's 4, balance 0, 2 1's, 2 balance 0, 1 0 0 1, 1 0 0, right? 9, yeah, 1 0 0 1. So everything will be 0. So second line is also completed. The control will be transferred to the third line. The third line we are saying A or B. The third line, the operation is A or B. It means from the truth table we can come to a conclusion that if at least one of the bits is 1, the answer is 1, or else the answer is 0. Right? Follow the same conclusion. So if you take these two numbers, 1, because one of the bits is 1, so answer is 1. So this is 0, 1, 1, 0, 0, 0, 0. So this is internal representation of what? A or B. A or B. So this is the binary number. Convert this into decimal number. So just add 2 to the power of 0 for all the 1 bits. 2 to the power of 2, 2 to the power of 3. Right? 8 plus 4 plus 1, which is equal to 30. Right? So here the output will be displayed. What? In the console we will get 30. That's what we got here. We go back here. That is what we got 30. This many things are happening inside. We just write a program, and this program has to be saved with the respective Java extension, right? After the saving, it needs to be compiled. After compilation, JVM Java virtual machine comes into picture, and this Java virtual machine will generate a thread. This thread will take control of the main method, and each and every instructions will be executed. The first instruction on top of, while executing the first instruction, a memory is getting allocated internally. Memory is getting allocated in the form of binary numbers. This actual decimal number is converted to binary number. Likewise, the second instruction also says to create a memory for the decimal number 9. Internally, this is how the memory will be created for the decimal number line, right? The third operation is we are saying try to find A or B. Perform a bitwise operation or bitwise operation. So this is what the OR bitwise operation does. What the truth table says, if you find at least one value as 1, the output is going to be 1, right? Same thing I have done here. By combining 2 bits, if at least one of the bits, value of one of the bits is 1, the answer is 1, right? 0, in this case 1, because here we have 1, here we have 1, so this is 1, so everything is going to be 0, right? After converting this, I am getting the value as 13. This will be displayed in the console. Same thing I got here. Right? With just one click, we are getting this answer, but these are the internal things that is happening behind the scenes. As simple as that. This is a simple understanding about what the bitwise OR operator, right? Bitwise OR. Likewise, we have a truth table for bitwise AND. Same example we will take. Same example, same truth table. Truth table for bitwise AND is going to be little different. So A, B, when I say A and B, zero, 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 one, 1, 0, 1, 1. Very simple. Or means if at least one of the bits is 1, the answer is 1. But un says if at least one of the bits is 0, the answer is 0. In this case, at least one of the bits is 0, answer is 0. At least one of the bit is 0, answer is 0. At least one of the bits is 0, answer is 0. So no bits are 0, so answer is always 0. Completely opposite. It talks about once, if at least one of the bits is 1, the answer is 1. If at least one of the bits is 0, the answer is 0. Simple, right? If you ever had to find the calculation, same calculation by using bitwise AND operator, just change the symbol. Change the symbol, right? And run. Output is 1. Output is 1. So we will analyze why it is 1. Very simple. Same values, right? The values are fixed, right? So let me copy and paste the same box. Right? So instead of performing OR operator, now I am performing AND operator. So I am using this symbol. Right? What the truth table says, if at least one of the bits is 0, the output is 0. At least one of the bits is 0, the output is 0. Right? Do the same thing. See, both bits are 1, so output is 1. One of the bits is 0, 0, 0, 0, 0, 0, 0, 0. Right? So this is the output that I got. Output in the form of binary number. Convert this to decimal number. Obviously, the answer is going to be what? 1. That is what we have got here. Internally, same operation again. Again, from the beginning, what it does, right? These things happens in the beginning. Compiler will come into the picture, JVM will come into the picture, JVM will try to get access to the main method, and each and every instructions will be executed. On executing each and every instruction, a memory will be created, right? And the calculations will happen internally, and the output will be displayed in the console. Same operation. Right? So this is what we call it as what? Bitwise AND operator. So this is the truth table for bitwise OR. This is truth table for bitwise AND. Truth table for AND operator. And we have completed this. Next one is bitwise XOR operator. So XOR operator, understanding this truth table is very easy. Same thing. A, B, A. This is symbol to represent XOR operator. Right? It says values are like 0, 0, 0, 1, 1, 0, 1, and 1. Right? When you find the same values in same values, the answer is 0. For different values, the answer is 1. Makes sense, right? Same values 0, 0. If it is 0, 0, same value 0. 1, 1, same values, answer is 0. For different values, answer is 1. This is a truth table. So simply I can illustrate it like for same values, answer or output is 0, right? And for different values, answer is 1. Right? Let us take the same example and we will just change the symbol. Instead of ampersand, we will just give this symbol. Run this. So we get the output like 12. Right? Let us understand whether the 12 is the correct answer or not. Same, since we haven't changed any values, let us take the same example. A and B. Same example. And now we are trying to perform the XOR operation. A gap B. So truth table says if it is same, if you are finding same value, 0. This is 1. This is 1. 0, 0, 0, 0. Convert this. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on. You need to consider only the powers of 1. Right? So 2 to the power of 3 is equivalent to 8. 2 to the power of 2 is equal to 4. The answer should be what? 8, 9, 10, 11, 12. We are getting 12. Let us see the system is also getting the same answer. 12. Makes sense? So this is what the XOR operator talks. So we have covered 3 operators. So we will see this bitwise complement and this left shift operator and this right shift operator. So all this concept of these operators we'll see tomorrow, right? So after understanding this, we will get a clear conclusion about what? About the bitwise operators.